Hi, everyone. Welcome to my final defense on novel models for improving operational efficiency of transit systems. Let's begin. Here is the outline for today's talk. At first, I would like to provide an introduction about the background of my work. Modern-day transit system is composed of different modes, as illustrated in this figure. On one end, public transit systems run fixed routes on reliable schedules, yet inefficient when ridership is low. On the other, private ride-hail services respond instantly, but are costly for the users. Between these extremes lies paratransit, demand-responsive transit, and microtransit. In my dissertation, I have focused on identifying critical operational inefficiencies for different transit modes and provide solution for them. Between 2014 and 2018, U.S. bus systems lost significant amount of riders irrespective of the size of urban area. At the same time, annual operating subsidies climbed past $40 billion. This growing gap between cost and usage tells a clear story. Today's fixed-route buses are increasingly out of sync with riders' needs. In 2019, COVID delivered a sudden decline in ridership across virtually every market. Although some recovery has taken place, overall ridership remains well below their pre-pandemic peaks, and the shape of demand has shifted. Notably, demand-responsive transit has grown from a niche service into a meaningful slice of the market, accounting for roughly 1 in 10 unlinked passenger trips today. Just as agencies were struggling with declining ridership during COVID, transit budgets upended. Between 2020 and 2022, combined operating and capital costs jumped by more than double. Yet the sharpest spike wasn't on busy bus or rail, it was in demand response transit, where per-mile operating expense on the DRT surged by nearly 3/4. When we zoom into agency operations, two troubling trends emerge. First, vehicle revenue miles have dropped after COVID and have plunged since. Second, on the demand response side, per-trip costs are nearly double the price of a taxi or TNC ride. In other words, our scheduled buses are riding empty, and our flexible shuttles are burning budget. So where do we go from here? In response, I focused on improving these operational inefficiencies in fixed and on-demand transit modes, which will be discussed in the subsequent slides. Now I'm going to discuss our first topic, which is semi-flexible bus with advanced reservation. Let's look at the pros and cons of the conventional public transit. Conventional public transit operates efficiently in dense urban areas, such as New York, where buses run on fixed routes and reliable schedules, and per-trip costs remain reasonable. But in low-density regions, such as Utah, buses often drive empty, stop at locations with no passengers, and idle at empty stops to catch up with the schedule. These underutilized bus routes are the focus of our study. A big challenge in the underutilized bus routes is the long walking distance to and from closest stops. How do we improve on this? We can simply add more stops. Consider the route in the left-hand side figure, where a rider has to walk nearly half a mile from origin to stop based on the current stop locations. However, if we add more stops to the system, the walking distance for that passenger reduces to half, as you can see the right-hand side figure. Therefore, by adding more stops, we are reducing the walking to make transit more accessible, which will eventually make public transport more attractive to users. However, there is a problem with adding stops to an existing route. Although driving time stays the same when we try to increase more stops to the system, serving added stops increases dwell time at each stop. So even with the same 36 minutes of driving in the above circular routes, visiting 13 stops instead of 5 pushes the tour from 39 minutes to 44 minutes due to added dwell time to serve the additional stops. As a result, although adding more stops reduces the walking, it slows the bus and reduces service frequency. Now, how can we add more stops without extending the tour duration? We achieve this by allowing the bus to skip stops without demand and take shortcuts, as shown in the System 2 on the right-hand side animation. However, to achieve this, passengers must plan ahead by giving advance notice of their intent to use the system. So how much farther downstream the bus can skip stops as we require longer advance notice? As shown in this animation, longer notice period helps the bus to skip more stops, which allows us to add more stops to the network. But this comes with a trade-off Longer notice period requires passengers to plan earlier and adds more variability in the bus arrival times. Putting it all together, we want to convert a conventional bus route into a semi-flexible system to add as many stops as possible while ensure with high probability that it does not exceed the original tour duration and honor the passenger reservations made before the specified notice period. To tackle this, we first build an analytical framework on a stylized circular route. Then we extend these ideas into a simulation-based framework applied to real-world bus routes in Maryland. Let's start with the analytical model. We assume passenger origins and destinations scatter uniformly along a circular route, and each rider uses the nearest stops. Based on these assumptions, we derive key proposition that gives the probability any given stop goes unused, which grows as we add more stops. Let's discuss the notations used in the analytical model. We denote by zeta sub nk the time saved when the bus skips k consecutive stops. We illustrate this on a circular route with stops n equal to 12 and up to 2 consecutive skips, m equal to 2. Zeta sub nk is the time difference between the arc and the chord. Let x sub k count how many times the bus skips exactly k stops in a tour. As shown in this example, x sub k can have different realizations in a tour, which makes it a random variable. We also define m as our cap on the maximum number of skips. Accordingly, all derivations are conditioned on the event. A sub nm, which ensures number of consecutive stops skipped, does not exceed m. Based on x sub k, we can model the tour duration as the full drive plus dwell time at stops minus the sum savings from skipping stops. As shown in the figure, the tour duration is a random variable because it is a function of x sub k random variables. To analyze the tour duration, we derived a joint probability mass function of x sub k random variables. Its derivation is challenging because x sub k random variables are not independent. The number of times we skip 4 stops impacts the number of times we skip 2 stops, and vice versa. This PMF lets us compute expectations, variance, and most importantly, the CDF of tour duration, which we need to formulate the first constraint. Recall that we also have the second constraint, which says that if a stop is requested, that stop must be visited with high probability. This is why we also model the arrival time at each stop. Using the joint PMF of x sub k, we can compute the expected arrival time, the variance, which we need to formulate the second constraint. So, how exactly do we ensure the second constraint? We construct the confidence interval for the arrival. It is this blue line. Recall that since bus can skip at most m stops or downstream stops that are a tau minutes away, the request needs to arrive before the starting of the red line, which guarantees that passenger requests to use a stop are served with high probability. Now we can formalize the problem. We maximize the number of stops n under 2 chance constraints. The semi-flexible bus tour duration stays within the fixed system tour duration with high probability, and every booked stop is served on time with high probability under the notice period. We also cap the maximum number of skips to capital M. To build our solution approach, we consider a circular route model where we prove 2 intuitive properties of zeta. For a fixed number of stops, zeta increases as the number of consecutive skipped stops increases. Conversely, for a fixed k, zeta decreases as n increases, approaching 0 as n goes to infinity. We use the properties from the previous slide to derive an upper bound, n bar sub m. The purpose of the upper bound is to achieve a bounded feasible region. Then we propose a grid search to find the optimal solution. We start in the upper right corner and intelligently explore the feasible region to find an optimal solution. Since we need to use a bottom-up approach to find the upper bound, we then derive a closed form upper bound that allows us to more quickly identify the previously discussed upper bound. Lastly, we analyze the computational complexity of our proposed grid search algorithm. Even though we are working with a limited number of points, the runtime of the algorithm is exponential. The reason this is the case is because computing the CDF to check the constraints requires us to find all possible bus routes, and their number grows exponentially. To improve computational efficiency, We apply dynamic programming to further tighten our original upper bound n bar sub m. Specifically, we formulate the problem as an unbounded knapsack problem, which allows us to find a tighter bound n star sub m. As shown in this proposition, this tighter bound n star sub m further reduces the feasible region we need to explore. We conducted sensitivity analysis with respect to two key parameters: probability of a stop not being used and the notice period. Lower utilization of stops in System 1 helps adding more stops in System 2. We also found longer notice period results in more stops in System 2. If we want to apply our analytical model directly to real-world routes, it is not possible due to arbitrary shapes of the route and non-uniform spacing between the existing stops, as shown in the red line route in Allegheny County. To address these complexities, we employed our simulation-based optimization model, where given the passenger OD and candidate stops, we add new stops to the route by minimizing passenger walking. In the simulation-based network, we reformulate the objective as minimizing expected walking distance rather than maximizing stops, subject to the same chance constraints on tour duration and arrival time at stops as used in the analytical model. To evaluate the objective function, we utilize sample average approximation as a proxy of expectation, and a greedy heuristic where at each step we simulate adding each remaining candidate stop, measure the average walking distance over demand scenarios, and pick the one with best improvement. To evaluate the tour duration constraint efficiently, we model tour duration as log normal distribution with unknown mean. We update the prior parameters sequentially using these equations. Using the updated parameters, we can check the constraint for tour duration using this equation. Arrival time constraints are managed similarly by modeling arrival times as log normal distribution under a conjugate normal inverse gamma prior. The prior parameters are updated using the sequential observation of arrival time at stops. Consequently, we use these parameters to evaluate the arrival time constraints using this equation. We tested our simulation-based optimization framework on Allegheny County routes. The animation shows results from the red line where we compare the fixed routing in the top left versus the resulting semi-flexible system with varying advance notice. As advance notice grows, more stops can be added to the system since the bus can take more shortcuts, while reducing the walking distance significantly. We also got substantial improvements in the blue line. The animation shows results from the blue line where we compare the fixed routing in the top left versus the resulting semi-flexible system with varying advance notice. When the advance notice is extended to 30 minutes, the number of stops on these lines increases by approximately 160%, leading to a substantial decrease in passenger walking distance by about 27%. To summarize, we have introduced a semi-flexible bus system that skips empty stops by advance reservation and takes shortcuts. We proposed an analytical model based on circular routes to provide the theoretical validation of the proposed semi-flexible bus system. We also proposed a simulation-based framework to apply the proposed semi-flexible bus system in real-world routes. Testing on real-world routes in Allegheny County, Maryland, we found that routes that were underutilized and have layout more conducive to shortcuts showed significant improvements in adding stops. However, 7 out of 10 routes did not show any improvement, for example, the yellow line. In the case of the routes that are more like a straight line, skipping a stop doesn't allow us to reduce driving time. The contributions of this research are the following. We formulated a probabilistic optimization model for designing a reservation-based semi-flexible bus system with explicit bounds and a custom grid search algorithm that provides optimal solution. We also developed a scalable simulation framework using greedy stop selection and sequential Bayesian learning for real-world routes, which showed substantial improvements when applied to Allegheny County routes. We have published a paper based on our work in the transportation science. I'm going to talk about our second topic on integrating dial-a-ride with TNC. Let me provide some background on the dial-a-ride services in the U.S. The Americans with Disabilities Act mandates transit agencies to provide dial-a-ride services to people whose disabilities prevent them from using fixed routes. The dial-a-ride services are coordinated by transit agencies who contract several local companies to provide these services. These dial-a-ride trips are scheduled at least a day in advance by specifying two things: the pickup and drop-off locations and the pickup or drop-off time. To make the dial-a-ride services more affordable for the users, dial-a-ride fare needs to be comparable to conventional transit. However, the actual cost of dial-a-ride trip is extremely high. For example, a DAR trip in King County Metro in Washington State costs about $80. As a result, the dial-a-ride operations are heavily subsidized, and dial-a-ride companies are under constant pressure to reduce operating costs. This motivates the development of efficient algorithms to route and schedule dial-a-ride trips. The development of algorithms to efficiently route and schedule dial-a-ride vehicles is often referred to as dial-a-ride problem. In a dial-a-ride problem, the goal is to find a set of minimum cost routes in order to satisfy a set of transportation requests. We have shown here an instance of the dial-a-ride problem from Challenger Transportation, with 1,000 requests that used MRM software to route and schedule these requests into 75 routes. The dial-a-ride problem has been extensively studied since the 1970s. However, it is noteworthy to mention that dial-a-ride problem is an NP-hard problem in terms of computational complexity, which means it is extremely difficult to solve, and the largest instance of optimally includes only 8 vehicles and 144 trips. As a result, real-world dial-a-ride problem instances with thousands of trips are tackled using various heuristics that quickly provide quality solutions that are nearly optimal. Since dial-a-ride problem deals with finding minimum cost routes, it is important to talk about how demand impacts dial-a-ride cost to better understand its impact. Let's consider this simple example with 2 riders. In this route, the passenger 1 is picked up first and then passenger 2, whereas passenger 2 is dropped off before passenger 1. Since the requests here facilitate ride-sharing, the cost of this route might be reasonable. Now, if we look at the second case, passenger 1 is picked up and then dropped off, and then passenger 2 is picked up and then dropped off. Here, pickup and drop-off locations of passenger 2 are far away from the rest of the demand, and it would result in excessive costs since the driver has to go extra miles to serve this request, which may be more expensive than serving this trip alone by Uber or Lyft. Therefore, from this example, it is evident that if demand facilitates ride-sharing, the cost per trip might be reasonable. Otherwise, it might be even more expensive than transportation network companies. Based on this fact, we can hypothesize that dial-a-ride company can reduce the operating costs by outsourcing them to transportation network companies. In the previous 2-rider example, we have seen that requests that are not compatible with the rest of the demand may incur extra costs. This mainly happens due to 2 reasons. In the case of temporal outliers, it increases the operating hours. And in the case of spatial outliers, it increases the driving miles. This phenomenon can be further illustrated through an example dial-a-ride route and schedule. On the left, we can see the geographical plot of the route, and on the right, the step function plot shows that load of the dial-a-ride vehicle, and bar below the step function plot shows the driving and idle time in green and red, respectively. It is evident from the geographical plot the origin and destination for the trip in the Northeast are far away from other demand locations. Furthermore, it is an early morning trip, so the vehicle has to leave early from the depot to serve this trip and then wait for a while before it can serve the next requests. As a result, if we outsource this trip, we may have to pay some money to TNC. However, we can save more by outsourcing this trip from the reduced routing distance and duration. This example suggests that integration of dial-a-ride with TNC could be a viable approach for reducing the dial-a-ride operating costs. Therefore, the objective of our research is to develop a framework that can identify outlier trips and outsource them to TNC. The methodology we developed in this study was heavily influenced by the size of the dataset for our study. We have utilized real-world data acquired from Challenger Transportation, which contained over 1,000 requests. In this figure, you can see the spatiotemporal distribution of demand in our dataset. The demand data contains 1,057 trips on a typical day selected by Challenger Transportation. Most of the trips are away from the depot and occur between 9 a.m. and 5 p.m. The temporal distribution of the trips shows a bimodal distribution, with peaks occurring around 9 a.m. and 2 p.m. If we further look at the demand distribution, the biggest generator and attractor of trips is Silver Spring, followed by Hyattsville and Rockville. To understand the trip characteristics, we can look at the summary statistics and distribution of trip duration and distance. The box plot and histogram of trip duration and distance indicate that the trips are relatively short, with a median trip duration of 12 minutes and a distance of 8 miles. Given the size of the dataset in our research, we proposed the two-stage framework that is outlined on this slide. In the first stage, we developed an integer programming formulation for dial-a-ride problem with trip outsourcing, which optimizes each route from MRMs individually and provides optimal solution within a reasonable amount of time. In the second stage, we developed an improvement heuristic that considers reinsertion of trips that were initially designated for outsourcing by the integer program solver. The multi-route heuristic also considers reinsertion and exchange of the remaining dial-a-ride trips among the routes to further reduce the operational cost. In our proposed integer programming framework, we considered the trade-off between dial-a-ride cost and TNC cost to decide which trips to be served by dial-a-ride and which trip to be outsourced to TNC. Our integer programming formulation extends from classical dial-a-ride problem with changes highlighted in blue. The goal of the objective function in our integer program is to minimize the total operating cost, which consists of fixed cost, routing cost, idle time cost, and TNC cost. The constraints ensure whether trip is either served by DAR or outsourced, enforce precedence and window adherence, bound vehicle loads, route durations, passenger ride times, and variable domains. The reoptimization of the MRM's routes is conducted by solving the proposed integer program that we have discussed in the previous slides. The routes are analyzed one at a time to identify and outsource outlier trips so that the combined dial-a-ride TNC cost is minimized. In this way, the integer program is applied to all MRM's routes individually and returns the optimized output routes after outsourcing outlier trips to TNC. Let's look at the high-level summary of savings resulting from the first stage of our framework. About 28% of the routes improved either by partial outsourcing, where part of the route got outsourced, or by full outsourcing, where all the trips in the route got outsourced. The savings from these routes are about 80% of the total savings. When we look at the distribution of costs for the routes without TNC integration and routes with TNC integration, we found that the cost of the reoptimized routes with TNC integration was significantly lower than those of MRM's routes. We further analyzed the cost breakdown before and after TNC integration. Although we are paying TNC $2,200 to serve 81 trips, we save $3,500 in operational costs by doing this, resulting in a net savings of $1,290, which is 5.3% of the total operational cost. In the next few slides, I am going to talk about the second stage of our framework where we developed a multi-route improvement heuristic. In the first step of the heuristic, it considers the insertion of the initially designated TNC trips as well as reinsertion of the remaining dial-a-ride trips in all the routes. The basic process of reinsertion is illustrated with an example. Let's say the solution from the integer program for a route has identified trip 8 for outsourcing to TNC at a cost of $50. Before we actually outsource it, we can see whether we can reinsert it into one of the other routes and serve it for less than $50. Here, trip 8 from this route is reinserted in before and after the drop-off of trip 3 in another route at a cheaper cost than outsourcing. In the second step of the multi-route heuristic, it considers exchange of trips among routes. In our trip exchange procedure, we first check if there is any service time conflict between trips to be exchanged. Then we consider all possible exchange between trips to find the best exchange with minimum routing costs. The trip exchange process is illustrated with this simple example. Here we exchange trips 8 and 4 since it resulted in minimum cost routes after exchanging. The proposed multi-route improvement heuristic was applied on the re-optimized routes from the first stage, and the savings breakdown from the improvement procedures are shown in this table. After applying the multi-route improvement procedure, we found that the number of outsourced trips reduced due to reinsertion, whereas the savings increased significantly. The additional savings from the improvement heuristic is about $467, which resulted in 2% more reduction in the operational cost. In summary, This research considered identifying and outsourcing dial-a-ride trips to TNC with the goal of reducing the overall service delivery cost. We developed a two-stage framework to address this problem. First, we formulated a single-route dial-a-ride with trip outsourcing as an integer program to re-optimize individual routes. Second, we developed a multi-route heuristic that considers reinsertion and exchange of trips among the routes. The proposed framework was applied to a data set obtained from a mid-sized paratransit company in Maryland, yielding significant cost reductions. From the sensitivity analysis, it was revealed that the mid-size operator can reduce the operating cost by 7% based on the original cost and up to 13% when the TNC discount is 30%, which is equivalent to taxi cost. The main contribution of our research can be summarized as follows. Our research is the first one to consider and optimize the cost trade-off between dial-a-ride and TNC. Previous studies have considered dial-a-ride TNC integration when the dial-a-ride vehicle gets delayed. Or when the dial-a-ride vehicle capacity is exceeded, however, none of the previous studies explore the integration when the dial-a-ride vehicles are available. We considered this in our study and developed a two-stage algorithmic framework to solve this problem. We published a paper based on our research in the Transportation Research Part E. Now I'm going to talk about our last topic on evolution of fixed transit to microtransit in Annapolis. This is basically a problem that I have worked on during my internship at IT Curves. Before 2024, Annapolis, like many small and mid-sized U.S. cities, relied on fixed route transit. That means buses follow predetermined routes and schedules, and passengers adapt to that schedule. Annapolis then converted their two underused routes, purple and orange routes, as shown on the left, into a microtransit service with 237 on-demand stops, as shown in the right-hand side figure. So what is a microtransit service? Microtransit is demand responsive. Instead of following a fixed route, vehicles are dynamically routed among the stops based on passenger requests submitted through a smartphone app. Why Annapolis transition to microtransit services? The first clear advantage is coverage. Because microtransit can support more stops, we get better spatial coverage and shorter walking distances on average. Instead of walking far to a few high-capacity stops, riders can usually walk a shorter distance to a neighborhood stop. Second, ride times can be more direct. Fixed route buses often stop at locations even when there's nobody boarding or alighting, which adds dead time. With microtransit, stops are only served when they're needed. So in principle, we can avoid some of the inefficiency of circulating through empty stops. So how does the microtransit system work in Annapolis? Passengers now use the Transego mobile app developed by IT Curves to submit trip requests specifying their origin and destination on the trip request screen. The system assigns nearby stops and informs the passengers. After the passenger accepts the stop assignments, the system announces the trip plan to the rider bi-dynamically, grouping compatible requests into shared vehicle routes. To power the app-based microtransit service, IT Curves developed Microtransit Scheduling Machine, MTSM, for dynamic routing and scheduling microtransit trip requests. MTSM dynamically integrates new trip requests with the existing pool of unserved or in-progress trips, forming an instance of the microtransit routing problem, MRP. The legacy algorithm workflow to solve an MRP instance is shown in this figure. The legacy algorithm used a parallel insertion heuristic, which scans each vehicle's current route to find a feasible pickup time. Then, for each vehicle, it tries to insert the pickup and drop-off into the existing route, checking capacity constraints, ride time limits, and time windows for both new and already assigned passengers. If it finds feasible insertion positions for at least one vehicle, it picks the lowest cost insertion and updates that route. If no feasible insertion exists, the request is rejected. We now illustrate an example solution from MTSM. Here, we show a pickup drop-off sequence in a microtransit routing problem, where pickup is represented by green passenger marker and drop-off is represented by blue passenger marker. The route produced by MTSM is represented by a solid line with varying thickness indicating the vehicle utilization, load showing how the vehicle facilitates ride-sharing to optimize the route. To illustrate the dynamic trip processing in MTSM, The scheduling process for 2 consecutive requests in this sequence is shown in this figure. When passenger P1 requests a ride at 12:03 p.m., the system calculates a feasible pickup time, considering a 30-minute scheduling window. After solving the MRP within a 1-minute computational limit, an initial pickup time of 12:13 p.m. is announced. Subsequent passenger P2 requests a ride at 12:04 p.m., also prompting a recalculation of routes. With a 5-minute pickup window, the system revises passenger P1's pickup to 12:14 p.m. and schedules passenger P2 for pickup at 12:11 p.m. This real-time updating process demonstrates how requests and time windows are continuously managed by the MTSM. While legacy PIH algorithm was computationally efficient, it had a severe limitation. It processed requests one at a time without revisiting earlier decisions, preventing it from grouping compatible requests or optimizing entire route segments. This means once a trip is assigned to a vehicle, it stays there, leading to suboptimal routing and excessive vehicle miles traveled. However, this issue can be overcome in the math programming-based algorithm. This is illustrated with an example instance, where insertion heuristic led to suboptimal decision. As shown in the right figure, request 8 initially assigned in vehicle 2 before routing request 9 was moved to vehicle 1 after routing request 9, which resulted in better routes in math program in comparison to PIH. This motivates moving from a purely heuristic PIH to an exact optimization model in the loop. In the new algorithm, we replace the legacy heuristic method with a mixed integer programming model. When a new request arrives, we solve a multi-vehicle MIP that considers all active and pending trips at once, where the MIP can reassign trips across vehicles and resequence stops to further reduce the costs. Because we need to operate in real time, we impose a hard limit of 1 minute of solver time. If the MIP finds a feasible solution within that time, we adopt it. If the problem is too hard to solve within the limit, we fall back to the PIH solution, which is much faster. Most instances are solved comfortably within the 1-minute limit, as shown in this figure. So in practice, the hybrid behaves mostly like a MIP-driven system, with the heuristic as a fallback. This slide gives the full mathematical formulation of the mixed integer program to solve a microtransit routing problem instance in MTSM. The objective of the MIP is to minimize the total travel time across all vehicles, subject to traditional multi-vehicle routing problem constraints and additional constraints required for microtransit operations. Now let's look at the performance of the new MIPI-based algorithm in comparison to the legacy algorithm. We ran a log replay experiment using 1 month of real operational data. For each day, we replayed the exact same demand under both algorithms to ensure fair comparison. We compared the daily number of trips served by the orange and purple vehicles. For the orange service, the new method serves about 6% more trips per day. For the purple service, the gain is even stronger, around 19%. When we look at the miles traveled per trip, the new algorithm consistently reduced this number. On the orange service, it cuts VMT per trip by about 14%, and on the purple side, it is roughly a 31% reduction. Of course, reducing vehicle miles and increasing trips served raises the question, what happens to passengers' ride times? This slide compares ride time distributions under PIH and under the MIPI-based algorithm for both services. In both cases, ride times are longer in the MIP-based algorithm. This is not unexpected since the math programming-based approach consolidates multiple passenger requests into shared rides. However, the ride times are always kept within the maximum duration limit, which is 150% of direct ride time. Even with improved real-time route optimization, microtransit systems can become saturated under high demand. Currently, Annapolis Transit experiences a rejection rate of about 15% of the trip requests. To illustrate the saturation, we conducted a simulation involving 2 microtransit vehicles operating in Annapolis over a 3.5-hour period, which shows that increasing the demand to 25 passengers per hour leads to approximately 50% of requests being rejected. In such cases, relying exclusively on dynamic, on-demand operations becomes unsustainable, and transitioning back to fixed-route service may be necessary to maintain service reliability. To develop a contingency strategy for this scenario, we focus on redesigning the fixed bus route based on the demand observed in the microtransit service. We formulate the orienteering problem to select a subset of microtransit stops for inclusion in the fixed route, where we maximize the OD demand served within a specified tour duration. Our formulation generalizes the classical orienteering problem by assigning rewards to OD pairs rather than individual vertices. As shown in the figure, using detailed OD demand data collected during microtransit operations, we can solve the OD orienteering problem to get revised fixed route. Here is the formulation of the proposed OD orienteering model, which maximizes the rewards in the visited stops subject to classical orienteering problem constraints, in addition to constraints to track the OD reward. Using the microtransit stops and OD demand data, we redesigned the fixed routes by solving our OD orienteering problem. This table summarizes the key performance measures of the old fixed route system versus the new orienteering-based fixed route design. The tour durations remains the same because the city can extend operating time. On the orange route, the new design trims the average walking by 29%. The purple route shows a similar pattern with a 24% reduction. Coverage improves as well. If we use a quarter-mile walking threshold, which is a common standard in transit planning, the redesigned routes cover 5% more passengers on orange and 2% more on purple. In the next 4 slides, I'll show how these quantitative improvements look spatially, starting with the orange service. Here we focus on the original orange route. On the left, we can see the old orange route alignment. On the right, we can see the OD flow map for the top 10 OD pairs. Now here is the redesigned orange route, together with the new OD flow visualization. In the redesigned orange route, we removed lightly used stops, especially along the Gentry Eastport segment, which didn't contribute much to the observed OD flows. On the other hand, the northernmost section now includes 8 additional stops near downtown and a park. We now turn to the purple service, which covers a larger area. Here we start again with the legacy purple route on the left and its OD flow map on the right. Now here's the redesigned purple route together with the new OD flow visualization. On the left, we can see that the northwest loop is eliminated, which was a low-demand detour. Instead, we redirect that time to add coverage near key activity centers. Specifically, we provide more stops around Annapolis Mall, school, and supermarkets. In this part, we discussed how Annapolis transitioned from 2 underutilized fixed routes and moved to an on-demand microtransit service. The new microtransit service increased stop density and flexibility, but the legacy insertion Hurey's IDD-based algorithm resulted in suboptimal routes. To address this issue, we proposed an exact MIP-based routing model that reoptimizes all vehicle routes and schedules each time a new request arrives. Furthermore, since microtransit systems can become saturated under high demand levels, we designed a fallback fixed route service using an OD orienteering model built on microtransit origin destination data. Using November 2024 data, the MIP-based routing resulted in about 6% more daily trips, with 14% less VMT per trip for the orange service, and 19% more trips with 31% less VMT per trip for the purple service, compared to the legacy PIH algorithm. Furthermore, the redesigned fixed routes based on ODOP reduced average walking distance by 29% for orange and 24% for purple. The contributions of this work are as follows. We proposed exact MIP-based optimization model in a municipal microtransit system, operating in real time using a parallel insertion heuristic as a fallback option. We also proposed odd orienteering problem, which generalizes the classical orienteering problem by assigning rewards to OD pairs rather than individual vertices. The resulting paper from this work is currently in second-round revision at Inform's Journal on Applied Analytics. Let's summarize the overall work. In my dissertation, I have mainly focused on improving operational efficiency in 3 modes of public transport. For fixed-route buses, I have proposed a semi-flexible reservation-based system. I have developed an analytical model to theoretically validate the proposed system and a simulation-based model to apply the proposed system in real-world routes. For dial-a-ride services, I have proposed dial-a-ride TNC integration that helps to reduce operational cost of DAR operators by outsourcing outlier trips to TNC. I have developed a two-stage framework to improve DAR routes by identifying and outsourcing outlier trips to TNC. And for microtransit, I have proposed replacing greedy insertion heuristic with math programming-based routing algorithm and redesigning fixed routes when microtransit demand exceeds the saturation limit. I have developed an MIP-based algorithm to replace the legacy PIH-based algorithm and developed an OD orienteering problem to redesign the fixed routes based on microtransit stops and OD demand. And this is the list of journal articles I have published till now. That's all in my presentation. Thank you for your patience.